even more thermal review. Let's take a look at some more thermal questions, how our energy flow works, how enthalpy works, and all that good stuff. So number one, here we go. The reaction of making aluminum oxide is right here. It's given an enthalpy of that reaction and simple fill in the blank. So the reaction of this is blank, and therefore heat is blank by the reaction. So we have a bunch of different options. So exothermic, endothermic, thermoneutral, neither released nor is absorbed. So first we have to figure out exo or endothermic, and then we'll figure out released or absorbed. So how do we figure that out? What information's there? If you're focusing on the equation, you're focusing on the wrong thing. It's all about this, right? Enthalpy is heat flow, right? And specifically, are you losing it or are you gaining it? So if it's negative, it has to be exothermic. So these are all gone. Never even heard of thermoneutral before. So then, is the heat absorbed or released by the reaction? And I hope that you think that it would be released, right? That's the whole definition of exothermic. Exothermic is releasing energy, endothermic is absorbing energy. So there's the first quick multiple choice question. Number two, the value of change of H for the reaction below is negative 126. How much heat in kilojoules is released when 2 moles of NaOH is formed? So first, I could say this, so you realize this. This could be written right on the side, okay? Secondly, what this really is saying, per mole of this reaction, okay? For this reaction. So for every time this reaction occurs, it makes that much heat. So that links to 2 of these, and 2 of those, and 4 of these, and 1 of these, okay? Every one of these link to this amount. So what are they saying? They're saying that I have 2 moles of NaOH. So if I have 2 moles of NaOH, how I can show this work is simply this, is that this reaction, for every 4 moles of NaOH, I release 126 kilojoules of energy. Okay, that's how that works. So please realize that this amount of enthalpy is based off of this specific equation. Okay, and the answer is asking in kilojoules. I'm already in kilojoules, so that's great. So the answer is negative 63 kilojoules. Specifically, the reaction does say released, so you could potentially get away with saying 63 kilojoules of energy. Or you could say 63 kilojoules of energy released, and then you could actually spell out the word released. But hopefully you're understanding when you're given an enthalpy and then it's asking a new amount, that is how that works. It's the relationships of each mole ratio. Okay, so number 3, why don't we pause this video for a second after I read it, and we can try to figure this out on our own. So it says the value of change of H for the reaction below is negative 790. The enthalpy change accompanying the reaction of 0.795 grams of sulfur is blank. Okay, so first, quickly, this is saying this. So now what if I have 0.95 grams of sulfur? How much heat is going to be released? It is very similar to number 2. So let's pause it and see if we can figure that out. All right, hopefully we have this, or else, let's see how we do this. So I hope whenever we're throwing grams that your instinct is, I gotta convert that to moles. So I look at the periodic table. It's roughly 32.1 grams of sulfur. And now, guys, I'm in moles. So now, what is this reaction? This reaction is for every 790 kilojoules of energy, there are 2 moles of sulfur, right? There are 2 moles of sulfur. So that's how that works. So I just multiply and divide through. And I would get negative 11.7 kilojoules. And this time it does not ask if it's released or if it's absorbed, so the sign is really important on that one. Good. All right, number 4. The specific heat capacity of lead is 0.13 joules per gram Kelvin. How much heat in joules is required to raise the temperature of 15 grams of lead from 22 to 37? I hope this is screaming MCAT. Right, this one is a slam dunk. It is saying I have 15 grams of lead. It is saying that I have a specific heat capacity of 0.3, which is very small. We learned though metals have very small specific heat capacities because, reminder, what it does is it takes this much energy, 0.13 joules, to raise 1 gram 1 degree. So it doesn't take a lot because it's a metal. And then we can type this in a bunch of ways. At the end of the day, 37 minus 22 is 15. So we could either write 15 right here, or you could write 37 minus 22. Okay? And my Q is 29.3 joules. All right. So let's take a look at number 5. This one's a little different. This is where you have to start taking some of your knowledge of just chemistry and being able to apply some things. It says the specific heat of liquid bromine is 0.226 joules per gram Kelvin. So right there, I'm already thinking MCAT's probably an issue here, or going to be a solution. How much heat is required to raise the temperature of 10 milliliters of bromine from 25 to 27.30 degrees Celsius? The density of the liquid bromine is 3.12 grams per milliliter. What? Okay, so first, the minute it says specific heat, I gotta be thinking MCAT. So let's start there. You're gonna help start filling in some things for me. So what do I have for sure? All right, I'm gonna get to this one right here. So this is M. I don't know what that is yet, but I do know that C is this right here. Okay. And then my temperature. Okay, so here, don't freak out about this. This is in Celsius. This is Kelvin. This is truly the change in temperature. So it doesn't matter. It really doesn't. But at the end of the day, that's 2.3. So what I'm just going to do is 2.3 Kelvin. Because if I add 273 to each of these, and I add 273 and 273, add to that, it's going to still be the difference at 2.3. So what is my mass? I cannot simply put 10 grams in here because it's not 1 gram per milliliter. So what I need to do is a little extra math. It's not a big deal. I'm going to take my milliliters and I'm going to multiply it by the density. So bromine appears to be very heavy. I have 31.2 grams of bromine. So that is going to go right there. And now it's done. All right? My mass times my specific heat times my change in temp. And I get 16.2 joules. All right, so I hope that makes sense. A little twist, not a big deal, but a little bit of a twist. All right, let's take a look at the next one, number 6. So given the following reactions, and I have 2 of them here, and I have some enthalpy values, determine the enthalpy value of the formation of Fe2O3 with CO. I think I said formation. The enthalpy, determine the enthalpy of the reaction, not the formation. So I'm wanting this equation here, and I'm really wanting this. Okay, what is the enthalpy of that reaction? So I hope you're looking at this and going, this has got to be Hess's law. This has got to be Hess's law. So mentally or actually, you want to find something in here that's specific to each equation separately. So right away, I'm going to look here and I see the Fe2O3. I don't see it anywhere else in here, and I see it in there. Okay, so I'm just going to focus on that one. So what am I seeing? That's on the proper side. So I'm going to rewrite that. Do not get lazy on me. That's why I gave you space. So let's rewrite that one. So I did not have to flip it, so I will not take this. I will not take that as a negative. That stays. But now let's keep looking. I've used that as my anchor, and I want to compare it. And there's 3 of them there. So I need to multiply this by 3. So make sure you take your time and you're updating your problem. And because of that, that's multiplied by 3 in the top. It's very important to make sure that we're showing this so we see it all. All right, let's take a look at the second one. What's something unique in that problem? And frankly, maybe some other things in here are, but sometimes things add up or cancel, and this one screams out to me, the Fe3O4. There it is, okay? And again, it appears to be on the exact same proper side, meaning that this is a product, that's a product. So first step, write it out. There we go. Next step, check it out in the problem. There's 2 of these, there's only 1 of these. So now we deal with the magnitude. First it's direction, then magnitude. So I multiply everything by 2. And then I multiply that by 2. And in theory, this needs to add up right here. So I just double check it. That looks good. Okay. The CO, check it out, 9 to 8. So that means all of these would cancel out. There'd be 1 left. The CO2, there's 9 here. There's 8 here. Check it out. Good. Fe2O3, good. And then I have, oh, I wrote that down wrong. Wonder if anybody you noticed that beforehand. So I had 3 Fe's. To say that didn't add up. So 6 FEs cancels out. That's good. All right, so you can have it like this. If it's ever asked for actual work though, please, you got to show it. So I'm going to show that once. I'm going to model it well. So I have 3 times that first enthalpy value plus 2 times this second enthalpy value, and then show your units once. And I get a total of negative 59 kilojoules. And there I go. So Hess's law in action there. That one we didn't have to flip at all. We only were dealing with magnitude. Okay. Number 7. Given the data in the table below, change of H for the reaction is blank. So once more, before I even go on, it's asking for this of this reaction, and I'm asking for that. And then this time, they give me a bunch of formation equations. Formation equations. Quickly, before I go on, for example, what this means is that this is made from its elements at standard states. So that's how this one looks, actually. So it releases 986.6 kilojoules when this reaction occurs, as one example. Okay? One other example, an easy one, is water. Looks like this. And then I have half of an oxygen, and it releases that much energy. So when you're given specifics, suggestion, or I'm going to at least illustrate this well, is that these values correlate with each reactant or product. So I'm just going to fill these in just so I don't flip them. Honestly, this is a really good, this one's in order, but it's not always. This is a good way to approach it on a test because you might mix them up. Okay, so now I see them. I see the amount of my water, I see the amount of my H3ASO4, and so on and so forth. So remember, this is products minus reactants. Okay? So I'll make a little bracket. I'm going to come right down here. So I'm going to take my products. I have 2 waters. Please do not do the math beforehand. It's kilojoules. So there's my products right there. And then my reactants. It's not a bad idea. It's not a bad idea to write down what you get for each one, just to make sure it's not getting flooded and you're making some mistakes. So that's the amounts in the products and the reactants. So when it's all said and done, the overall enthalpy change is negative 130.4. All right. Only 2 left. All right, this one looks long, so let's figure out what's going on here. So it says the change of H for the solution process when solid sodium hydroxide dissolves in water is negative 44.4. When a 13.9 gram sample of NaOH dissolves in 250 grams of water, which is at 23 degrees, in a coffee cup calorimeter, the temperature increases. Determine the final temperature of the solution. Assume that the solution has a specific heat, the same as liquid water. Okay, so a couple things are going on here. One, I heard an equation. I really did. So this sounds like I have my NaOH. When it dissolves in water, I'm just going to illustrate this once, I'm going to have these ions. Okay? When it does, I have a change of H of 40.4, negative 44.4 kilojoules per mole. Okay, so what's the point of that? Well, this illustrates this equation right here. But I was told specific amounts. This is per mole. This is a specific amount. Okay, so what I need to do is get that specific amount into moles of NaOH. So I have 13.9 grams per mole. Sorry, just grams. Right? We know that it's 40. That's because 23 plus 16 plus 1, right? The molar mass. I have 1 mole. So this is how many moles of NaOH I have right now. Okay, so now if I asked you the amount of energy that resulted from that, I hope you could do that. This is, if you had 1 mole, I have basically 1/3 of a mole. So in chemistry, I would show that like this, where I would take my enthalpy for every 1 mole. I have negative 44.4 kilojoules. Right, I'm going to have about 1/3 of that. So I get about negative 15.5 kilojoules. Okay? So that's how much is released. Now, here is kind of the key to this. They have talked about specific heat capacities. So this is a great test question because of the fact that I would have to challenge you on what's all happening. But the fact that it says specific heat, okay, you got to be thinking Q equals MCAT. So whenever I'm doing this, I start thinking to myself, what information am I looking for? Well, first off, it says determine the final temp. So we're going to solve for change in T here. That means I need to know the rest of this, okay? So Q is joules, right? The only joules I have are right there. Okay, the only joules I have. And this is from the system. So you got to remind yourselves. I'm trying to zoom in here. If this is from the system, then I'd have 15.5 kilojoules for the water. Because the thermometer's got to read it. So the energy is going to go up in the water. Why is that so important? Because when I jump over here, I'm going to say I have 15,500 joules. Wait, what? 15,000? Yep, 15.5 kilojoules is 15,000. Why 15,000? Because I'm doing joules. Okay, so now, what is my mass? We've done this before. I have placed a salt in a certain amount of water. So I'm going to show this thoroughly so you understand. I'm taking the salt plus the water. Okay, here's the water, specific heat capacity. And then I'm going to do this in red. Do not write this. You could write it like this, where you're doing the final minus the initial. But the math of this would have to have distribution. You have to distribute everything, and that is more complicated. So instead, I'm going to take this whole thing, and I'm going to just solve for change of T. And then I will cross that bridge later when we need to solve for the final temperature. So I'm going to just slide this up. So here we go. Change in T equals 14.1 degrees Celsius, or Kelvin. Well, I could have had Kelvin, but I ended up doing it in Celsius here. So T minus 23, right? That's what that equals, right? The change in temp is the difference between these two. So my final temp is going to be 37.1. Okay. Tricky. Very tricky. What I would have realized, let's say you didn't know you had to do this in the beginning, okay? You would have hopefully realized at some point, though, that you needed to get that energy. So some of us may have made that mistake and brought that here, but that is if I had an entire mole. And this is specific. When you're given a specific amount, you need to find the specific energy, okay? So, final question of our final review, besides your take-home review. Determine the change of H for each situation below. So we'll do one at a time. A solution's heat released was determined to be 9856 joules, where 25 mils of 0.75 molar HCl reacted with 30 milliliters of 0.5 molar NaOH. What? So I don't understand what it's asking. Well, here's what it's saying, though. We're determining the change of H. That's what we're asking. So here's the first thing that we need to understand. I'm going to highlight this. Change of H always deals with joules or kilojoules per mole. Per mole. So I have to divide this. So when they give me in a number, I have to put this basically over the moles. So I need the moles of reacting. How many moles that react? So if I was going to really try to give you some good details of LR, okay, you need to know the limiting reactant amount of moles. So in this case, what they're doing, what they're screaming, is that they are screaming to find moles. So I will do HCl first. I'm going to put it in molarity equals moles over liters. Okay. That first one gets me 0.0188 moles of HCl. All right. Then I will do the base. So just assume that because it's a smaller amount, because you also have a different value of your volume. For the volume, the volume's different. And I get 0.015 moles of NaOH. So you're like, I don't know how to answer this. Well, if you actually did the equation, maybe we should write it out quickly. It's HCl plus NaOH gives you NaCl and HOH, or water. Right? Look at this. 1 to 1 to 1 to 1. So this is a 1 to 1 to 1. So that means I don't even have to do math. This is the least amount. So NaOH is the limiting reactant. So that means my change of H, excuse me, heat released, negative 98.56 joules over my limiting reactant of moles, and I get negative 657, and it would be 657,000, so I'm going into kilojoules. Okay, so the other thing I should have said is that signs matter. Plus, negative matter. Okay, for a change of H, it matters. All right, last problem. It says a solution's heat absorbed, so that's kind of important, was determined to be 98.56. Same thing, where 4.5 grams of ammonium nitrate is added to 50 mils of water. All right, so what does that look like? So this one's a little different, because when we do a salt, the idea of it dissolving is where the reaction's happening, okay? But what's happening here is that you are putting in 25 grams into water, so you're making a solution. So it's almost always assumed that the solution is already the limiting reactant. It's not a great assumption, but the way that these problems are written, it's almost always that way. So that means I need to get my moles again. This time I'm going to do ammonium nitrate. Also, guys, the fact that a problem gives you the molar mass, that is a huge hint. They want you to use it, okay? So I need to find moles, because again, I have a joule already. I need to divide it over an amount. All right, so I have 80 grams. And what I end up getting is about a third of a mole. Okay, so change of H equals plus, you don't have to necessarily write that, but I'm talking about the absorbed, right? Plus, and then I'm going to put it over my moles. And I get 34.4 kilojoules per mole. Again, that describes the entire reaction. So what these are saying in this first one is that this amount of energy was released when this many moles reacted. Well, clearly then I'm going to have more energy. Same thing. This amount of energy was absorbed when a third of a mole reacted. So when I have a full mole, it should be a lot more. Right? So all these problems, I'm just trying to show you all the different ways that we can be utilizing our enthalpies, our relationships, and how it all works with Q equals MCAT, Hess's law, enthalpy of formations. So I hope that helps. We'll continue to review. Hope everything's going well with this information.